So did we like this little activity the last 2 days?
Yes.
Yeah, okay. Unfortunately, we're not going to be able to be in the cool room today, but that's okay. We can tough it out. So the reason that we were doing this Play-Doh activity is to make sense of this next kind of volume topic. So far, we've only been taking a look at volumes when we revolve around an axis, right? We're always going in a circle. But there's other ways to calculate volumes of irregularly shaped objects. And one of them is a process known as cross-sectional volume. Are you guys familiar with that term, cross-section? You've probably heard it in like a science or biology class. How are you familiar with it, or what do you know about a cross-section? No idea? Okay, so if you were to, I need an object here. This is not very irregular. Anyway, I'll work with this, okay? So if you were to take this bottle and you were to slice it, like cut it this way, and you were to like pull it apart, open it up, you know what I mean by that? Okay? What shape would the cut look like? A circle, right? So the cross section is a circle. If you were to cut it and like spread it open, it would look like a circle. What we're going to do is take a look at different cross-sectional shapes, like squares or isosceles right triangles, some equilateral triangles, and a semicircle, like you guys did it with the Play-Doh activity, okay? So what we've talked about so far with volume is that if you were to revolve, okay, volumes of solids created by revolving something, whenever you are revolving, you are going in a circle, correct? Okay? And in order to find volume, you integrate area. So if we're forming a circle by revolving, we would find the volume by integrating the area of a circle, aka pi r squared. Okay, we've done that so far. But in our little activity here, we are not revolving, okay? We are cutting. We have a cross section. So our volume formula is not going to look like a circle, pi r squared. It's going to look like whatever area it is of that cross section. So for these different geometric shapes, in order to find the volume of these irregularly shaped objects with these different cross sections, we have to integrate the area of the cross section. And that changes depending on the cross-sectional shape. Does that make sense? Okay, revolving is a circle. You integrate the area of a circle. We are not revolving in this case, we're cutting, but we're still going to integrate the area. It just depends on the shape of that cut, or of that cross-section. So if you take a look at the first one, the cross-sections that are squares, these are the first ones we did. If you were to do squares all the way through your little activity, it would look something like that, right? We just didn't do it all the way through. And I know on ours, I think your top function is g of x and your bottom function is f of x. Is that right? Okay. In this example, they're kind of switched. Notice how the top function is f of x and the bottom one is g of x, okay? But it's still the same idea nonetheless. So if you were to find the area of this square, you would need the base of the square times the height, right? Side times side. But how can we represent that side length? Go ahead, Caitlin. Top minus bottom, right? In this case, the top function is f of x minus the bottom function is g of x. So notice how that's labeled in your little diagram there. The bottom or the base of that cross-sectional square is f of x minus g of x, and since it's a square, it's the same on the side, right? So the area, we could say, is the f of x minus g of x, and we are squaring that, right? The base times the height. F of x minus g of x times another f of x minus g of x, you get f of x minus g of x squared. So if that's how we can represent the area of the cross-section, how would we write the calculus notation in terms of an integral to find the volume? If that's the area, how could we find the volume of that object? Yeah?
Multiply it by your width of it, so it's just going to be x. So we can need to find the sideways
I don't know if we're necessarily multiplying by something. Let's see. Okay, up here we said to figure out the volume of an object, you have to integrate the area of that cross-sectional shape. We just said the area was f of x minus g of x squared. So what would the integral look like? And I'm sorry, Eric, if I wasn't understanding you correctly, but we're not necessarily multiplying by anything. Yeah?
I was just going to say that the integral, when you integrate it, it finds the sum of all the edges, and then you multiply by dx.
Oh, did you say multiply by dx?
Yeah.
I thought you said multiply by, I'm sorry, I couldn't hear you because of the fan. Okay, so we are multiplying by dx. Good. And then go ahead.
Well, then you put the sum of all the areas, so it's just
Okay, so the integral is another way to represent that sum idea, right? Remember when we did Riemann sums, we took all those rectangles, added them up, and that was the area under the curve, okay? This integral is another notation that can mean adding everything together. So what we need to do is we need to take all of these individual areas, all those little squares that you cut, and add them together, and that would give us the entire volume if we were to go all the way through from beginning to end. So we're going to integrate the area of that square. We're going to add them all up. Dx is just representing the width of each square, but that's kind of negligible, right? Because the slices are so thin, just like your paper is really thin. And then the bounds on the integral would just be whatever the beginning point and ending point, or sometimes the intersection points would be. Okay? So notice how in order to get the volume, we integrate the area. The dx is typical in any integral, unless it was a dy, and then we have that beginning and ending bound. Okay, so to get volume, you have to integrate area. Let's take a look at the next one. When we did isosceles right triangles, we had the base of the triangle, and then the height going up, and then the hypotenuse connecting them. Okay, so this is the base on your paper, on the Play-Doh piece, and then you go up and you have your hypotenuse. So how do we find the area of that triangle? How do you find the area of any triangle? Good, Caitlin? 1/2 base times height. Okay, so notice how the base is that f of x minus g of x, top function minus bottom function, but that is also the height as well. So we would have 1/2 and then f of x minus g of x squared, because we're multiplying the same base and height together. Does that make sense? 1/2 base times height? Okay, so if each cross-sectional cut of this object was an isosceles right triangle, to figure out the volume, we would have to integrate the area of that isosceles right triangle. Again, going from A to B. If you wanted to write the 1/2 in front of that integral, you could, because it's a constant. Okay, you can like factor or pull it out. Okay. Are we starting to see how to get volume? You integrate area. Okay, it all depends on the shape that you have. All right, let's try the next one. This one's a little trickier. We have an equilateral triangle. When you did this, the base of the triangle was on the Play-Doh, and then you cut from opposite corners to make that diagonal. What does equilateral mean again? You remember from geometry way back when? Yeah? All the sides are equal. So we could throw in those little tick marks. And if all the sides are equal, then, yeah? So are the angles, okay? And if there's 180 degrees in a triangle, then each angle is 60 degrees. Okay? Now, this is still a triangle nonetheless, right? So in order to figure out the area of this triangle, we still have to do 1/2 base times height. And based off of our little cross section here, we know the base, the part in the Play-Doh, is still f of x minus g of x, but the height is not that same distance. So we have to figure out what is the height in this case. So I wonder if we can try to think about this a little bit. Let's see. This, maybe we'll focus on this right-handed triangle over here. And we know this is a 60-degree angle. We're trying to figure out the height, so maybe I'll label that h. Is there some type of trig expression we could write that would somehow involve this 60 we know and the h we're trying to find? Can you think about your trig, like SOHCAHTOA? Sine, cosine, tangent? What do you think, Eric?
Just take sine of 60 is equal to h over f of x minus g.
Alright, so if we did sine, that would be opposite over, this one would be the hypotenuse? But, okay. So we'll do sine of 60 degrees is the opposite h over the hypotenuse, f of x minus g of x. Alright, now we're trying to figure out what h is, that way we can substitute it into our area formula. Do we know what sine of 60 is? Are we that good with our unit circle yet? Sine of 60 degrees? Good, Eric? Square root of 3 over 2. There you go. Alright, so this is the square root of 3 over 2. Alright, and in order to solve for h, let's go ahead and multiply the denominator to the other side. So we would have the square root of 3 over 2 times f of x minus g of x. And that expression is representing the height of any of the equilateral triangles that you cut. So let's go ahead and represent this area of the equilateral triangle. We have 1/2 times the base, which was f of x minus g of x. And then we got to multiply by the height, which we just found was the square root of 3 over 2, times another f of x minus g of x. So if we combine these together, it looks like we have the square root of 3 over 4 if we multiply the fractions together, and then an f of x minus g of x squared. So if that's the area of every single triangle you cut, we want to add all those together, aka integral. We're going to sum them all together just like our little rectangles from last year to find the volume. We doing okay? Alright. Our last one, we have the semicircles. So on the base in your Play-Doh, that was kind of representing the diameter of your semicircle. Okay, so the diameter was that f of x minus g of x from one end to the other end of the circle. How do you find the area of a semicircle? Yeah. 1/2 pi r squared. Alright, so in terms of our semicircles, we would have 1/2 pi, and then what is the radius? You think about that? Go ahead, Cameron. Right, if f of x minus g of x is the entire diameter, we need to cut that in half. So we would have f of x minus g of x, you could say divided by 2. Maybe you want to pull that 1/2 out front. Okay, but nonetheless, we do have 1/2 pi r squared. Maybe we can simplify this one like we did the equilateral triangle. If we're squaring this radius, we would have a 2 squared in the denominator, which would be 4. And notice how we could multiply that by the 2 in the other denominator, which would give us a 1/8 out front. And we would just be left with that f of x minus g of x quantity squared, if we cleaned it up a little bit. So that's how we can represent the area of every semicircle. If we want to find the volume, we're going to add all those up, aka integrate. Oh, can't see it. Okay, so these are kind of the 4 main cross sections that you might come across. We'll take a look at some other ones when we get through some of the examples, but it's still the same idea. You have to find the area of that cross-sectional shape, and we're going to integrate that to find the volume. Okay, so just so we can look at some patterns, can you take a look at the 4 volume formulas we just made, the 2 on the front and the 2 on the back? And what do you notice about some of those formulas? Can we make some connections or distinctions? Do you notice anything? Go, Caitlin. Okay, so they all have f of x minus g of x squared. Okay, that's a big one. They all revolve, or not revolve, they all involve, okay, integrating area of the cross section to find the volume. I don't know if there's really any other connection between the f of x minus g of x squared, because they all have like a different multiplier or constant value. Some of them have a pi, some of them don't. Okay, so I think this is the only one really, at least of the 4 that we've seen, that have all that in common. F of x minus g of x squared. Okay, so let's go ahead and take a look at an example here. Okay. We're going to pretend this region R was kind of like the one that you drew on your Play-Doh. You can use that as a reference if you want to. And if the cross sections were these different shapes, we're going to see what the volume of the solid would be, depending on how, or the shape that you would cut it. Okay, so cross sections are equilateral triangles. We need to integrate the area of an equilateral triangle, and then from there we'll use the functions as the f of x and g of x to make it make more sense for this example. So maybe you have to reference this. Okay, we'll eventually get good at knowing the different formulas. But what is the volume integral for an equilateral triangle? Can you reference one of the 4? Good, Caitlin? Uh-huh. Right. Okay, so we got to figure out top minus bottom. Looks like the top function would be the trig one. Oh, sorry. The top function would be the trig one of sine, and the bottom function would be cubic. So we would need sine of pi x. And if we subtract the cubic one, that would change all the signs. We would have a minus x cubed plus 4x. Right? You're subtracting the whole thing. What about the bounds? Good, Cameron? 0 to 2. Okay. So from here, we'll let the calculator do the work. These are definitely calculator type questions. We are using trig, so make sure you're in radian mode. Any takers? Go to Eric.
Yeah, 9.97.
9.978. We got something different? There's a lot going on. We might need to see how we type it in, yeah. 4.321? Maybe? All right, let's see. So we have Math 9, integral from 0 to 2. Let's see, we have the square root of 3 divided by 4. And then sine pi x minus x cubed plus 4x. And we got to square that dx. 4.321? Okay. Okay. So we're going to deal with the same region, okay, but this time maybe if we were to cut it, the cross sections were semicircles. We're going to see how that kind of changes the volume a bit. So we need to integrate the area of a semicircle related to the shape or region that we have. We're still going to have 0 to 2 on the x-axis. We're still going to have the dx on the end. It's just we got to figure out the area of that semicircle. So maybe you got to reference the 4 that we did, but we'll eventually get used to knowing which numbers go where. Remember, we already said all of these kind of have f of x minus g of x squared. It's just the number that differs, that constant value. So what about for a semicircle? What's our constant value? For the equilateral triangles, we have the square root of 3 over 4. Go, Caitlin. Pi over 8 or 1/8 pi. Yep, either one. And then we need f of x minus g of x squared. So it's the same sine of pi x minus x cubed plus 4x. Go ahead and let the calculator do the work. Any takers? Does it start with a 3? 3.918? Is the calculator our friend today? Is it working for us? Yeah? Okay. Let's go ahead and check out C. Cross sections are isosceles right triangles. So volume equals, we still have 0 to 2. We still have f of x minus g of x squared. What is our constant multiplier for an isosceles right triangle? Hey, Cameron? 1/2. All right, let the calculator do the work. Can we get our volume? Autumn, you want to give it a shot? Yep, 4.989. We doing okay? All right. And the last of the 4 that we talked about, what if our cross section was a square? We still have f of x minus g of x, that quantity squared. Do we have a multiplier if our cross section is a square? Technically it's 1, right? But you don't have to write that if you don't want to. So let's go ahead and find our volume. What's our volume for the squares? Good, Maddie?
9.978.
9.978. 4 for 4? Okay, so those are 4 typical ones. Notice how they all have that f of x minus g of x squared. The only difference is the multiplier, or that constant coefficient out front, okay? But that's not to say that we could have different cross-sectional shapes. Okay, sometimes they can throw in other ones as well. So if you take a look at the 2 at the bottom, notice how we're now dealing with rectangles. Okay, not one of the 4 that we talked about, but they still work the same way. We have to figure out what is the area of this particular rectangle for our region, and then we're simply going to integrate it. So maybe we'll draw a picture to help us kind of label things like we did before. Cross sections are rectangles whose height is twice the length of the base. So the base is normally what goes into the Play-Doh, okay, the one on the paper. So if the height is twice the length of the base, it's kind of a very tall rectangle, something like that. And if the base is the part in your Play-Doh then that's the f of x minus g of x portion, okay, top minus bottom, based off your graph. How can we label the height if it's twice the length of the base? Yeah. 2 times that, yep. 2 times f of x minus g of x. So now that we have this rectangle labeled, how would you find the area of that rectangle? Good, Eric?
Just 2 times f of x minus g of x squared.
Yes, we need base times height, and notice how if you multiply those together, we're going to have another f of x minus g of x squared. So let's go ahead and integrate that from 0 to 2. Okay, we're relating this back to the region R at the top. We would have 2 times f of x minus g of x squared. Maybe instead of f of x and g of x, we'll use the actual equations. Sine of pi x minus x cubed plus 4x squared. Okay. So in this case, the idea of that twice the height, that is signifying your coefficient or your multiplier out front. $19.957. Sound good? Okay. In F, we have a similar rectangle, but this time the height is 1/3 the length of the base. So it's a very small rectangle. Can we think about what the volume integral might look like? Very similar picture to the one we drew over here, just a 1/3 instead of a 2. Okay, notice how the 1/3 would be that coefficient, and we would have the f of x minus g of x squared portion. Still going from 0 to 2. $3.326 ish. Yeah? Perfect. We doing okay? Alright. We're going to save the last page for tomorrow. I know we still have a little bit of time left, but I want to make sure that we can do this in its entirety and not have to cut halfway through. Alright. Hopefully you're still working on some of those homework problems. Okay, we are going to finish this section tomorrow, which means I would think your homework will be due on Tuesday. Okay? And if you guys have any questions on the homework, you can always ask in here. We can go over anything you need to. Alright?